Okay, this is going to be the lesson video for section 13.2, which is derivatives and integrals of vector functions. So let me go ahead and display the notes. All right, so let's go ahead and talk about this. This is actually a short lesson, but actually a crucially important lesson. We're going to use what's in this section here very, very frequently throughout the rest of the semester. So we're going to define, now that we know how to take limits of vector functions, we can define a derivative. And the derivative is going to allow us to determine something about the direction that a curve is going through three-dimensional space, which turns out to be super important. Okay, so to build up the idea of a derivative of a vector function, recall from single variable calculus that if you have a domain x and then a range which is a y as a function of x, and you represent that as a two-dimensional curve, the function curve, if we wanted to know the derivative as we are changing in the x direction, we would start at the value of x I want the derivative for. We'd go some distance h away down the path of the input of the domain, and that would give me another point on the function curve. So I could plug x into the function and get f of x. I could plug x plus this distance h into the function and get f of x plus h as the y. And then I could just apply the slope formula from algebra to get the slope of this red line. This is called the secant line between the 2 points, right? So this is the change in y, f of x plus h minus f of x, divided by the change in x, which is just h. So this red expression represents the slope of the secant line. And then what we did was we made the h get smaller and smaller and smaller, and that meant that these points got closer and closer together until when they are negligibly close, they formed this blue tangent line. And we defined the tangent line to be tangent to the curve, going in the same direction as the curve right at this value x. And then we said that the derivative of the curve is equal to the slope of that tangent line. So it represents how the instantaneous rate of change of y as we make changes in x, okay? And so to do that, we just took the limit as this distance h approached 0 of the difference quotient structure to get f prime of x. This was the derivative and our symbol for that. All right, so now we have multivariable calculus vector functions, right? So the domain is now the parameter, right? And we know the output is potentially a three-dimensional vector that has x, y, z components that traces out a space curve. It's actually the output of the vector function is the position vectors to those points, and they trace out points like this. So imagine we did the same thing. We want to find the derivative, something that's like the derivative of the vector function. We're going to define that as r prime of t, which, by the way, I should use a vector notation there because that's a vector. These are also vectors, so you should add those to your notes. These are also vectors. All right. So what is the derivative of a position vector? All right, well, if we were to start by having the position vector to the starting point and then move a distance h along the curve, okay, just like we did over here along. Now here we changed x or h in the direction along the domain. The domain here is the parameter, so we add a little h to the parameter t. That gets us to a new location, and the output would be this vector r t plus h. So the difference in the outputs would be the r vector at t plus h minus the r vector at t. And then if we divide that by h, we can we actually have to do a vector subtraction. So this would be the position vector of r at t plus h, this red vector. That's this one. And then when you subtract off this one, the difference would be this blue vector. Okay, so the difference here, you can think of it kind of as the secant line here. That would be this vector minus this vector. So you get this blue vector here. Okay, and then if we allow h to approach 0 and take the limit, then we're getting a vector which is basically roughly in the direction, we actually switch to blue, it's in the direction of the curve, and it represents how fast it's changing as we, for each individual unit parameter change in the t. Okay, so it's kind of got an analog to what we did there, but this is the definition. limit definition of the derivative of a vector function. We just replace, we have the input vector at the initial point, the point a little bit further down, and then we take the limit of the structure. So what's important geometrically is, although it's kind of harder to visualize, if these points are brought close together, then this derivative vector is actually in the direction that the curve is traveling in three-dimensional space. And so we therefore call that the tangent vector. So the tangent vector is another name for r prime, the vector r prime, as a function of t. Okay? Now usually, because we want to not introduce something related to the magnitude, we're interested just in the direction that the curve is moving. And when we need that, we want to have this tangent vector, but with unit length. And that is defined as the unit tangent vector. So what we do is we find the tangent vector, which is our prime vector, and then we just divide by its length to force it to be a unit length, right? And that gives us what's called the unit tangent vector, which is typically written with a capital T to separate it from the parameter t. So capital T stands for unit tangent vector, and it's also a function of t. All right? Now, even though the limit definition is conceptually how this is working, in practice, we don't actually compute it that way. We use these theorems, which are proved in the textbook. If you have a position vector or function rt, which has component functions xt, yt, and zt, then if you go through the limit definition carefully on each of these things, the derivative vector, the tangent vector, is equal to the derivative of the x component as x, the derivative of the y function component for y, and the derivative of z function separately. Right? So let's say I wanted to find the unit tangent vector for this given vector, and we wanted to evaluate it specifically at the point when the input parameter t was 2. So this is actually, once we do one, you'll see it's actually not that complicated. It sounds more complicated than it is. So first we're going to find the r prime vector. Let me write it a little bit better. R prime, and then that's a vector. It's a function of t, and so I'm just going to take the derivative as the x, y, and z component, treating t as the variable. So the derivative of 3t would be 3, the derivative of t squared would be 2t, and the derivative of 0 would be 0. So this is called the tangent vector. Okay? And then if I want to make the unit tangent vector, I just need to find the magnitude of that vector by taking the square root of the sum of the squares, which would be 3 squared and then 2t squared, right? So generically that would be 9 plus 4t squared. However, since we know we want to do this at a particular point, once we've taken the derivative, at any point after that, we can just go ahead and plug the value in. So if I wanted to find the tangent vector at the point 2, I could just go ahead and plug the 2 in for the t. So that would give me 3, 4, 0. And therefore the magnitude of that vector would be the square root of 3 squared plus 4 squared plus 0 squared is 5. Right? So then therefore that means that the unit tangent vector, which is usually abbreviated t, is just going to be the normalized version of the tangent vector. So I could just take, generically it would be this. If I didn't have this, if I didn't have a t specified, I would write it like this. I would say it's 3 2t 0, but with a magnitude of the square root of 9 plus 4t squared. But what I really am after, what the problem's really asking me is what is the tangent vector at 2? And so I would just take this vector 3, 4, 0, and then just divide it by 5. So in fact, it would be 3/5, 4/5, 0. This is the answer to the problem, okay? I would probably not even do this part, right? Because if they gave me a t, as soon as I'm done taking the derivative, it's okay to plug the value in and then just work with the numbers. If I needed something that could be at any t, then I would have to express it with expressions involving the parameter. And so what this is there is some vector here, right? If you were to plot the space curve, it has some shape, right? And then at t equals 2, you're at a certain point. And then this vector is moving in the direction of the curve at the point t equals 2. All right, so we're going to do that operation, especially the one we just did here with a given t value. We're going to do that a lot, so really important to get good at that. A couple of rules for derivatives. So they obey things that are similar to other derivative rules. Let me blow this up a little bit. So if you have two vector functions that you're adding, and you take the derivative of the sum of the vector functions, you can take the derivatives of each thing separately. So just like with derivatives, if you do adding and subtracting, you can do terms individually, right? If you have a constant, it can move inside or outside of the derivative operation, just like with regular functions. If you have two functions that are both functions of t, however, one of them is a vector function, one of them is a scalar function, then you have to do the product rule, just like we do for derivatives. And you would have the derivative, the scalar derivative here, times the original vector plus the original scalar function times the derivative of the vector, the vector derivative. If you are taking the derivative of a dot product of functions, it turns out that the product rule, something like the product rule applies as well. It's going to be the derivative of one of the vectors dot the non-derivative version of the other, the non-derivative version dot the derivative version, so kind of like the product rule. And the same thing is true for cross products. So it turns out you can show that that works as well. And if you have a compound function, so you have a vector function, which is in terms of another function. I actually haven't seen any examples of this in the homework that we're assigning, but in that case, you could basically take the derivative of the outside function and then multiply it by the derivative of the inside function, the same as we do for anything else. This enables us to do substitution. So we'll see examples of that one later, I believe. Okay, and then the last thing I want to mention for today is, because definite integrals are smooth versions of Riemann sums, which can be computed using limits, and limits are defined for vector functions, you can take definite integrals of vector functions, okay? So for example, if you have a vector function, so these are intended to be vector functions. Let me put little vector symbols there. So if I have a vector function r of parameter t, and I want to integrate all the values of the vector function from a to b, from t equals a to t equals b, that is the same as adding up a whole bunch of little kind of like Riemann sums, essentially, right? And because this is a vector function, the x, y, and z would separate out into separate components. And because limits can be applied to x, y, and z separately, it means you can take the integral of the x and the integral of the y and the integral of the z functions separately. So the only takeaway from this, we're not going to use that as much right now, but we'll see it more later, is just like with a derivative, if you're taking a derivative here, you have x, y, z, you just take the derivative of the x, derivative of the y, and the derivative of the z. If you have an integral, it works the same way. If you're taking the integral of a function, you just separately do the integral of the x, the y, and the z functions. All right. All right, so that's pretty much it in section 13.2, a small but very important, that unit tangent idea is really important, so we're going to see that quite a bit throughout the course.